What if I told you that the secret code behind every smartphone and computer on Earth was actually discovered by a 17th-century philosopher wearing a massive periwig? Today, we unlock the life of Gottfried Wilhelm Leibniz, the man who didn't just invent calculus, but envisioned the entire digital future we are living in right now. Part 1: The Foundation of a Polymath. Most people know him as the other guy who invented calculus. But Gottfried Wilhelm Leibniz was a man who tried to organize the entire sum of human knowledge into a single logical system. He was a lawyer, a diplomat, a philosopher, and a mathematician. Today, we look at the life and the incredible mind of the man who arguably shaped the digital world more than any other person in history. Gottfried Wilhelm Leibniz was born on July 1, 1646, in Leipzig, Germany. His father was a professor of moral philosophy, but he died when Leibniz was only 6 years old. This left the young boy with a massive inheritance, his father's library. At a time when most kids were learning basic arithmetic, Leibniz was teaching himself Latin and Greek so he could read ancient texts. By the age of 12, he was reading advanced scholastic philosophy. He once said that he would walk through the woods and contemplate whether he should follow the moderns or the ancients. Leibniz was a true child prodigy. He entered the University of Leipzig at age 15. Imagine that. While most of us were navigating high school, he was earning his bachelor's degree in philosophy. He finished his doctorate in law by age 20, but the University of Leipzig refused to give it to him because he was too young. Did he give up? No. He went to the University of Altdorf, presented his thesis, and they were so impressed they offered him a professorship on the spot. He turned it down. He wanted a life of action, diplomacy, and discovery. Before we dive into his first big mathematical breakthrough, it is important to understand his mindset. Leibniz believed in a characteristica universalis. This was his dream of a universal language where every concept was represented by a symbol. He believed that if we had this language, two philosophers having a disagreement would simply sit down with a pen and paper and say, "Let us calculate." He wanted to turn all human thought into mathematics. His journey into serious mathematics actually started late, during a diplomatic mission to Paris in 1672. He met the great Christian Huygens. At that time, Leibniz didn't even know much about formal geometry or advanced algebra. Huygens gave him a test problem: find the sum of the reciprocal of triangular numbers. To understand this, let us look at the formula. The sum of the series from n equals 1 to infinity, of 2, divided by the quantity n, times the quantity n plus 1. Leibniz realized that this was a telescoping series. He broke it down. Adding the terms up, he found that all the middle terms cancel out. You are left with 2 times 1, which equals 2. Huygens was stunned. He told Leibniz that he was a natural. This sparked a fire in Leibniz that led directly to the creation of the calculus we use today. While Newton approached calculus through physics and flux ions, Leibniz approached it through logic and notation. He spent years obsessing over the perfect way to write things down. He knew that the right symbols make the brain work faster. Think about the notation for a derivative. We write dy divided by dx. Or for an integral, we use that long, stylized s symbol. That was all Leibniz. He chose that s because it stood for summa, the Latin word for sum. He viewed integration as an infinite sum of infinitely thin rectangles. Let us look at a basic derivation he worked on. If we have a function, y equals x to the power of n, the derivative is found by looking at the change. He used the concept of differentials, which are infinitely small changes. He would write dy equals n times x to the power of the quantity n minus 1, times dx. If we rearrange that, we get the familiar dy divided by dx equals n times x to the power of the quantity n minus 1. He also gave us the product rule. If you have two functions, u and v, the derivative of the product, u times v, is written as d of the quantity u times v equals u times dv plus v times du. Notice how elegant that is. Leibniz believed that the beauty of the formula reflected the beauty of God's design. He was deeply religious and felt that by discovering the laws of mathematics, he was reading the mind of the Creator. He often worked through the night, barely sleeping, writing on scraps of paper that he would leave scattered around his room. He was the definition of an eccentric genius. He even invented a carriage with a built-in desk so he could calculate while traveling on bumpy roads. One of the most fascinating, fun facts about Leibniz is that he was a bit of a fashion icon, or at least he tried to be. He was famous for his massive periwigs. Some say he wore them to hide a small bump on his head, but mostly it was the style of the time. He was a man of the courts, moving between kings and queens, trying to unite the Catholic and Protestant churches while simultaneously trying to build a calculator. Yes, a calculator. Long before digital computers, Leibniz built the stepped reckoner. It was a mechanical calculator that could add, subtract, multiply, and divide. It used a special gear mechanism called the Leibniz wheel. While Pascal had built a machine that could add, Leibniz wanted more. He wanted a machine that could handle the heavy lifting of multiplication through repeated additions automatically. The derivation of the gear ratios for this machine was a masterpiece of engineering. He had to account for carrying numbers across multiple columns. He spent a fortune of his own money trying to get the brass gears machined perfectly. Unfortunately, the technology of the 1600s wasn't quite precise enough, and the machine often jammed. But the logic was flawless. The Leibniz wheel was used in mechanical calculators all the way until the mid-20th century. Leibniz also had a strange obsession with China. He studied Chinese philosophy and was fascinated by the I Ching. He noticed that the hexagrams in the I Ching could be represented as a series of zeros and ones. This led him to rediscover and formalize the binary system. He believed that binary was the ultimate representation of creation. 1 represented God, and 0 represented the void. Let us look at how he explained binary. In the decimal system, we use base 10. But in binary, or base 2, every number is a power of 2. For example, the number 5 is written as 101. This means 1 times 2 to the power of 2, plus 0 times 2 to the power of 1, plus 1 times 2 to the power of 0. Which is 4 plus 0 plus 1 equals 5. He was so proud of this that he proposed a medal be struck to honor binary. He didn't know that 300 years later, every single computer, smartphone, and satellite would run entirely on his ones and zeros. He saw the spiritual in the mathematical, and the mathematical in the spiritual. Leibniz was also a pioneer in the study of energy. In physics, he disagreed with Descartes. Descartes thought that the quantity of motion, which we call momentum, was the most important thing. But Leibniz argued for what he called vis viva, or living force. He derived this by looking at falling objects. He showed that the living force was proportional to the mass times the square of the velocity. In modern terms, we write this as E sub k equals 1 divided by 2 times m times v to the power of 2. This was the birth of the concept of kinetic energy. He realized that while momentum is conserved, there was another force that stayed constant in the universe. If you are enjoying this deep dive into the life of the man who saw the world through numbers, make sure to like this video and subscribe to the channel. As we move through his life, we see a man who never stopped. He was the librarian for the Duke of Brunswick. This sounds like a quiet job, but for Leibniz, it was an excuse to travel all over Europe researching genealogy. He used these trips to meet every scientist and philosopher he could find. He was a networking king before the term existed. He corresponded with over 1,100 different people. His letters are a treasure trove of scientific history. But with all this fame and intellect came one of the greatest controversies in the history of science, the Calculus War. This conflict would darken his later years and create a rift between British and continental mathematics that lasted for a century. Part 2, The Calculus Revolution. As we move deeper into the 1670s, Leibniz was no longer just a student of mathematics, he was becoming its pioneer. While living in Paris, he experienced a mathematical awakening. He spent his days in libraries and his nights scribbling notes that would eventually change the way we calculate everything from planetary orbits to the stress on a bridge. This is the period where the differential and integral calculus was truly born. To understand Leibniz's genius, we have to look at the problem mathematicians were trying to solve. For centuries, people struggled with curves. Finding the area under a straight line is easy. Finding the slope of a flat roof is easy. But what happens when the line curves? What happens when the speed of an object is constantly changing? This was the problem of tangents and the problem of quadratures. Leibniz had a unique realization. He saw that these two problems, finding the slope and finding the area, were actually two sides of the same coin. This is what we now call the fundamental theorem of calculus. He arrived at this not through physics, like Newton, but through a deep analysis of sequences and sums. Let us dive into a specific derivation he performed. Leibniz looked at a curve and imagined it as a polygon with an infinite number of infinitely small sides. He introduced the differential, which he denoted as dx. In his mind, dx was a quantity that was not zero, but smaller than any assignable quantity. Imagine a function, y equals f of x. Leibniz wanted to find the slope at a specific point. He looked at the change in y, which he called dy, and the change in x, which he called dx. The slope is simply the ratio, dy divided by dx. To derive the rule for a power, say y equals x to the power of 2, he did something brilliant. He replaced x with x plus dx and y with y plus dy. This gives us the equation, y plus dy equals, in parentheses, x plus dx to the power of 2. If we expand the right side, we get y plus dy equals x to the power of 2 plus 2 times x times dx plus dx to the power of 2. Since we know that y equals x to the power of 2, we can subtract y from the left and x to the power of 2 from the right. This leaves us with dy equals 2 times x times dx plus dx to the power of 2. Now, Leibniz made a bold move. He argued that because dx is infinitely small, the term dx to the power of 2 is incomparably smaller and can be ignored. So, we have dy equals 2 times x times dx. Dividing both sides by dx gives us dy divided by dx equals 2 times x. This was revolutionary because it was a mechanical process. You didn't need to draw complex geometric figures anymore, you just needed to follow the rules of the symbols. Leibniz spent a massive amount of time refining this notation. He tried many different ways to write the sum of all y's. He eventually settled on that long, elegant S-shape, the integral sign. He wrote the integral of y dx. This notation is so perfect that we still use it in every classroom today. Newton's notation, which used dots over letters, was much harder to use for complex problems. This is why, even though Newton might have started his work earlier, it was Leibniz's language that the world eventually adopted. One of Leibniz's most beautiful results is the Leibniz formula for pi. He discovered this by looking at the integral of 1 divided by the quantity 1 plus x to the power of 2. The integral from 0 to 1, of 1 divided by the quantity 1 plus x to the power of 2 dx, is equal to the arctangent of x, evaluated from 0 to 1. The arctangent of 1 is pi divided by 4. Leibniz showed that this could be written as an infinite series. Pi divided by 4 equals 1 minus 1 divided by 3, plus 1 divided by 5, minus 1 divided by 7, plus 1 divided by 9 and so on forever. This is a stunning connection between the odd numbers and the geometry of a circle. It is an alternating series. While it converges very slowly, its simplicity is a testament to Leibniz's ability to find deep patterns in simple sequences. Aside from pure math, Leibniz was also a master of logic. He is often considered the father of symbolic logic. He developed a system where logical statements could be processed like algebraic equations. He used the symbol A and the symbol B to represent concepts. He would write A is B to mean that the concept A contains the concept B. For example, if A is man and B is mortal, then the statement all men are mortal is expressed by the inclusion of the properties. He even experimented with using prime numbers to represent fundamental concepts, so that complex ideas could be multiplied together. This was essentially the first attempt at a computer database schema. But Leibniz wasn't just sitting in a room thinking about abstract symbols. He was also a man of practical inventions. During his time in the Harz Mountains, he was tasked with improving the silver mines. The mines were constantly flooding. Leibniz, ever the optimist, proposed using windmills to power pumps that would clear the water. He spent years in the cold, muddy mountains trying to get his engineering projects to work. He even designed a horizontal windmill that would work regardless of the wind direction. While many of these projects failed due to local politics and technical limitations of the era, they show that Leibniz was a hands-on genius. He didn't just want to know the truth, he wanted the truth to be useful. In fact, he once said, "It is unworthy of excellent men to lose hours like slaves in the labor of calculation which could safely be relegated to others if machines were used." This was his justification for the stepped reckoner. He saw human potential as something that should be spent on creativity and discovery, not on boring, repetitive tasks. An interesting anecdote from this time: Leibniz was so busy that he reportedly once went for months without leaving his chair for more than a few hours of sleep at a time. He would eat his meals while working, and sleep in his chair so he could wake up and immediately resume his calculations. He was a man possessed by the need to understand everything. He also had a very strange habit when it came to people. He was incredibly polite and would rarely argue in person. Even if he thought someone was completely wrong, he would try to find the grain of truth in their argument and build upon it. He called this the principle of harmony. He believed that everyone had a piece of the puzzle, and his job was to put the pieces together. However, this peaceful nature was about to be tested. By the late 1670s, word was spreading about a mathematician in England named Isaac Newton who was also working on a new kind of mathematics. Leibniz had exchanged a few letters with Newton through Henry Oldenburg, the secretary of the Royal Society. In these letters, Newton was cryptic. He sent Leibniz an anagram, a jumbled set of letters, to hide his methods, fearing that Leibniz might steal them. Leibniz, being transparent and perhaps a bit naive, replied by openly sharing his methods of differentials and integrals. He didn't realize that he was walking into a trap that would lead to a lifelong feud. At this point in our story, Leibniz is at the height of his powers. He has formalized the rules of calculus, the power rule, the product rule, and the quotient rule. He has discovered the binary system. He has designed a mechanical computer. And he is starting to formulate his philosophy of the best of all possible worlds. But why do we call it Leibniz's calculus, and not just calculus? It is because of the power of his notation. Let's look at the chain rule, which is essential for modern physics. Leibniz wrote it as dy divided by dx equals dy divided by du times du divided by dx. It looks like fractions canceling out. Even though they aren't exactly fractions, the notation makes the logic so intuitive that it is almost impossible to get wrong. This was the gift Leibniz gave to every student who followed him. Part 3: The Great Dispute and the Logic of Matrices. As we enter the 1680s and 1690s, Leibniz was at the peak of his intellectual influence. But as his fame grew, so did the shadows of conflict. This period marks the beginning of the most famous rivalry in the history of science, the battle between Gottfried Wilhelm Leibniz and Isaac Newton over who truly invented calculus. It is a story of national pride, secret letters, and two geniuses who simply couldn't get along. But before the war broke out, Leibniz was still making massive leaps in pure mathematics. While he is most famous for calculus, he was also the man who laid the groundwork for what we now call linear algebra. He was one of the first people in the West to use determinants. Leibniz wanted a way to solve systems of linear equations without doing all the manual substitution. He looked at equations where you have multiple variables, like x and y, and multiple constants. He began to organize the coefficients into a grid-like structure, what we now call a matrix. Let us look at a simple system of two equations. Suppose we have a sub 1 times x plus b sub 1 times y equals c sub 1, and a sub 2 times x plus b sub 2 times y equals c sub 2. Leibniz realized that the solution for x and y depended on a specific relationship between the coefficients. He derived that the denominator for the solution would be the quantity a sub 1 times b sub 2 minus a sub 2 times b sub 1. This value is exactly the determinant of a 2 by 2 matrix. He wrote about this in 1693, nearly 150 years before the term matrix was even coined. He was essentially trying to find a logic of arrays that would allow a person to calculate the value of multiple unknowns simultaneously. Why does this matter? Because every time a computer renders a 3D graphic in a video game today, it is performing millions of matrix multiplications and calculating determinants using the very logic Leibniz first scribbled down in his letters. He saw that structure and pattern were the keys to unlocking complex problems. Now, let us talk about the calculus war. In 1684, Leibniz published his work on calculus in a journal called Acta Eruditorum. His paper was titled A New Method for Maxima and Minima. It was brilliant, but it was also very brief and difficult to understand. Newton, across the English Channel, was furious. Newton had been working on his method of flux ions since the mid-1660s, but he hadn't published it. He had only shared it with a few close friends in private manuscripts. When Newton saw Leibniz's publication, he felt his intellectual property had been stolen. The Royal Society in London, which Newton eventually presided over, became a battleground. The English mathematicians backed Newton, while the continental mathematicians, led by the brilliant Bernoulli brothers, backed Leibniz. The accusations were nasty. Newton's supporters accused Leibniz of seeing Newton's private papers during his visit to London and simply changing the notation. Leibniz, in turn, defended his honor, pointing out that his approach was fundamentally different. Newton's calculus was based on motion and physics. He thought about a point moving along a path. Leibniz's calculus was based on the geometry of the infinitely small. He thought about sums and differences. Newton used the notation of dots. For example, the derivative of x was written as x with a dot over it. Leibniz used the notation we have already discussed, dx. The dispute wasn't just about ego, it was about the future of math. Because of this fight, British mathematicians refused to use Leibniz's notation for over 100 years. They stuck with Newton's dots. As a result, British mathematics actually fell behind the rest of Europe, because Leibniz's notation was simply much easier to use for advanced problems. Despite the stress of this conflict, Leibniz's mind never slowed down. He turned his attention to what he called the dyadic or binary system again, refining it into a formal mathematical tool. He saw binary as a way to prove that everything can be created out of nothing. He even tried to use math to solve the problem of human disagreement. He worked on a universal calculus of logic. He believed that if we could assign a number to every human concept, we could use a formula to determine the truth of any statement. For example, if the concept animal is represented by the number 2, and the concept rational is represented by the number 3, then the concept man would be 2 times 3, which equals 6. Then, to check if man is an animal, you would just see if 6 is divisible by 2. It was a beautiful, if somewhat naive, dream. But it was the first step toward the Boolean logic that makes modern software possible. Leibniz was also a pioneer in the field of probability. He was fascinated by games of chance and legal problems involving risk. He realized that the expectation of an outcome could be calculated mathematically. If a prize has a value A, and the probability of winning is P, then the fair price to pay for the chance is P times A. He applied this to insurance, annuities, and even the probability of a witness telling the truth in court. He was trying to mathematize the very fabric of society. An amazing, fun fact about Leibniz is that he was a bit of a pack rat. He kept every single piece of paper he ever wrote on. Today, his archives in Hanover, Germany, contain over 200,000 pages of handwritten notes. Scholars are still finding new ideas in his papers that haven't been published. He lived in a world of ink and parchment, but he thought in a world of algorithms and data. If you are fascinated by how a 17th-century quarrel over calculus ended up defining the language of modern science, please like this video. Subscribe now to join us as we continue this journey through the history of genius. Leibniz's social life was just as complex as his math. He was a diplomat for the House of Hanover. His job was to ensure that the electors of Hanover became the kings of England. He succeeded, but at a high personal cost. When his employer, George Lewis, became King George I of Great Britain, he told Leibniz to stay behind in Germany. Why? Because the Calculus War had made Leibniz so unpopular in England that the new king didn't want the plagiarist in his court. Leibniz was left alone in Hanover, feeling abandoned by the very people he had helped rise to power. But even in his isolation, he continued to work on his most profound philosophical work, the monadology. In this work, he tried to derive the nature of the entire universe from a set of logical axioms. He argued that since the universe is a unified whole, it must be made of simple substances that have no parts. These are the monads. He used a mathematical analogy. Just as a point has no dimension but is the foundation of a line, a monad has no physical extension but is the foundation of reality. He also developed the principle of sufficient reason. He stated that nothing happens without a reason why it should be so rather than otherwise. This principle is a cornerstone of both science and philosophy. It is why we look for laws of nature. If the universe was random, math wouldn't work. Leibniz believed the universe was the most mathematical place possible. Let us look at one more of his mathematical gems, the Leibniz rule for differentiating under the integral sign. If we have an integral where the limits and the function both depend on a variable, say alpha, the formula looks like this. The derivative with respect to alpha, of the integral from u of alpha to v of alpha, of f of x and alpha, dx. Leibniz showed that this equals the integral of the partial derivative of the function, plus the function evaluated at the upper limit times the derivative of the upper limit, minus the function evaluated at the lower limit times the derivative of the lower limit. It sounds complicated, but it is an incredibly powerful tool for physicists. It allows you to see how a system changes over time even when the boundaries of that system are moving. Leibniz was a man who saw the connections between everything. He saw the link between a gear and a clock, a binary digit, and the soul of a human being. He was constantly looking for the harmony in the world. Part 4, The Best of All Possible Worlds. As we move into the final decade of the 17th century and the beginning of the 18th, Leibniz found himself in a strange position. He was arguably the most famous intellectual in Europe, yet he was increasingly lonely. His patron, Electress Sophia of the Palatinate, was one of the few people who truly understood his depth, but as the political tides shifted toward England, Leibniz was left behind in the dusty libraries of Hanover. It was during this time that he consolidated his most famous, and most controversial, philosophical theory, optimism. Now, in everyday language, optimism means looking on the bright side. But for Leibniz, the best of all possible worlds was a strict logical derivation. He started with the principle of contradiction and the principle of sufficient reason. He argued that God, being omniscient, could conceive of an infinite number of possible universes. Being omnipotent, God could create any of them. And being perfectly good, God would choose to create the one that was the best. But what does best mean in mathematics? Leibniz defined it as the world that achieves the maximum variety of phenomena with the minimum complexity of laws. Imagine a graph. If you have a set of points, there are infinite curves that can pass through them. But the best curve is the simplest one that accounts for all the data. In his work Theodicy, he used this to explain the existence of evil. He argued that even the negatives in the world are necessary for the overall mathematical harmony of the system, just as shadows are necessary in a painting to create depth. This idea was so influential that it defined the early Enlightenment. However, it also made him a target. The famous writer Voltaire later mocked Leibniz in his book Candide, where a character named Dr. Pangloss keeps insisting everything is for the best even while facing horrific disasters. But Leibniz wasn't being naive. He was trying to find a mathematical justification for existence itself. While he was debating philosophy with the greatest minds of Europe, he never stopped his mathematical pursuits. He became deeply interested in dynamics, a term he actually invented. He wanted to go beyond the geometry of motion and understand the forces behind it. He engaged in a long-running debate with the followers of René Descartes. Descartes believed that the total quantity of motion, which is mass times velocity, was conserved in the universe. Leibniz used a clever thought experiment to prove Descartes wrong. He considered two bodies. body A with a mass of 1 and a velocity of 4, and body B with a mass of 4 and a velocity of 1. Descartes would say they have the same quantity of motion because 1 times 4 equals 4 times 1. But Leibniz looked at how high these bodies could lift a weight. He showed that the work done was proportional to the square of the velocity. He derived the formula for vis viva, which we mentioned earlier, mass times velocity to the power of 2. He argued that it was this quantity, what we now call double the kinetic energy, that was the true living force of nature. This was a massive step toward the modern law of the conservation of energy. Leibniz also made significant contributions to the study of combinatorics. He wrote Dissertatio de Arte Combinatoria when he was very young, but he refined these ideas throughout his life. He wanted to find a way to calculate all possible combinations of any set of elements. He looked at the Pascal triangle, though he often found deeper properties in it than Pascal himself. He derived formulas for the number of ways to choose k elements from a set of n elements. He saw this as the alphabet of human thought. If you could break down every complex idea into prime concepts, you could use combinatorics to generate every possible true statement that could ever be made. One of his most practical, yet overlooked, achievements was his work on life contingencies. Because of his role in the court, he was asked to help manage the state's finances. He used his knowledge of probability and calculus to calculate how much money a state should set aside for pensions and insurance. He derived formulas for present value that are still used by actuaries today. He was essentially the first data scientist in history using math to predict human lifespans and economic stability. A fun fact about this period, Leibniz was so obsessed with efficiency that he proposed the creation of a global encyclopedia. He wanted all the world's knowledge to be indexed and cross-referenced so that no scientist would ever waste time rediscovering something that had already been found. He even suggested a universal library that would use a decimal-based sorting system, a precursor to the Dewey Decimal System. But as the years passed, the calculus war with Newton continued to drain his spirit. In 1712, the Royal Society in London published a report called the Commercium Epistolicum. It was supposed to be an independent investigation into who invented calculus. In reality, it was written almost entirely by Newton himself and his supporters. It officially branded Leibniz a plagiarist. Leibniz was heartbroken. He had spent his life trying to bring people together, trying to create a republic of letters where scientists shared everything for the common good. Now, he was being cast out. Despite this, he stayed productive. He wrote the Monadology in 1714, just 2 years before his death. It is one of the most dense and beautiful works of philosophy ever written. In it, he describes the universe as a pre-established harmony. Think of two perfectly synchronized clocks. They aren't connected to each other, but they always show the same time because they were designed by the same master clockmaker. That was his solution to the mind-body problem. Your mind and your body don't cause each other to move. They are just two clocks set in motion by God to stay in perfect mathematical sync. Leibniz's health began to fail in 1716. He suffered from gout and arthritis, likely from decades of sitting in cold libraries and traveling in damp carriages. Even on his deathbed, he was still taking notes. He was working on a history of the House of Brunswick that the Duke had been badgering him to finish for 30 years. Leibniz had kept expanding the project, going all the way back to the Dark Ages, because he couldn't help but look for the big picture. He died on November 14, 1716. His end was surprisingly quiet and lonely. At the time of his funeral, his reputation was so damaged by the fight with Newton that not a single member of the Royal Society or the Berlin Academy of Sciences, which he founded, attended his burial. Only his secretary followed the coffin to the grave. An eyewitness reported that he was buried more like a robber than what he really was, the ornament of his country. But while the men of his time turned their backs on him, the numbers did not. The symbols he created, the binary code he championed, and the vis viva he discovered were waiting for the rest of the world to catch up. Part 5: The Vindication of a Visionary. Though Gottfried Wilhelm Leibniz was buried in near obscurity, the seeds he planted in the fertile soil of mathematics and logic were destined to grow into the modern world. For decades after his death, the shadow of the calculus war loomed large. In England, mathematicians stubbornly clung to Newton's flux ions and dot notation. But on the European continent, the power of Leibniz's language was becoming undeniable. The Bernoulli family, Leonhard Euler, and later mathematicians like Lagrange and Laplace all used Leibniz's dy divided by dx and the integral sign. Why? Because Leibniz had designed his math to be operational. He wanted the symbols to do the thinking for you. By the early 1800s, even the British realized they were falling behind. A group of Cambridge mathematicians formed the Analytical Society specifically to bring the Leibnizian methods to England. They jokingly said they wanted to support the principles of pure deism over the dot age of the university. This was the first great vindication of Leibniz. His notation wasn't just a different way of writing, it was a more powerful way of thinking. It allowed mathematicians to tackle the heat equation, fluid dynamics, and electromagnetism in ways that Newton's notation simply couldn't handle easily. But the biggest surprise was yet to come. In the 1840s, George Boole developed Boolean algebra, the logic of true and false. This was exactly what Leibniz had dreamed of with his Characteristica Universalis. Boole had unknowingly completed the work Leibniz started in his messy study in Hanover. Then came the 20th century. As engineers began to build the first electronic computers, they looked for a way to represent information. They found it in Leibniz's zeros and ones. Let us look at a specific mathematical legacy, non-standard analysis. For nearly 200 years, mathematicians were nervous about Leibniz's infinitesimals. They called them ghosts of departed quantities, because they weren't quite zero but were smaller than any number. In the 1960s, a mathematician named Abraham Robinson proved that Leibniz's logic was actually perfectly sound. He developed a rigorous system where infinitesimals exist as hyperreal numbers. This means that Leibniz wasn't just fudging the math to get the right answer. He had a deep, intuitive grasp of a mathematical reality that took the rest of the world 2 centuries to formally prove. Let us look at another derivation that has Leibniz's fingerprints all over it, the Taylor series. While Brooke Taylor is credited with the series, Leibniz was already working on the idea of representing functions as infinite sums of polynomials. The general form of a Taylor series for a function f of x, centered at a, is the sum from n equals 0 to infinity of the nth derivative of f, evaluated at a, divided by n factorial, multiplied by the quantity x minus a, to the power of n. Leibniz's work on the derivatives of products and his notation for higher-order derivatives, writing the second derivative as d to the power of 2y divided by dx to the power of 2, made these infinite expansions possible. He saw that any smooth curve could be broken down into an infinite sum of simpler parts. Aside from the math, Leibniz's fun fact legacy is everywhere. Did you know he was one of the first people to suggest that the Earth has a molten core? Or that he proposed a theory of biological evolution long before Darwin, suggesting that species change over time through gradual transitions? He even designed a system for desalinating seawater and developed a plan for a global health organization to track diseases. He was a man who lived in the 17th century but whose mind was firmly planted in the 21st. He once wrote, "The present is big with the future." He knew that his ideas were too big for his own time. He was a polymath in the truest sense, a man who saw no boundaries between science, religion, math, and law. If we look back at the calculus war now, we see that it wasn't a matter of who was right. Both Newton and Leibniz were giants. But Newton was the last of the great ancients, using geometry to explain the physical world. Leibniz was the first of the great moderns, using logic and symbols to create a digital world. The best of all possible worlds may have been mocked by Voltaire, but in the world of modern physics and optimization theory, Leibniz has the last laugh. Today, we use variational calculus, another field Leibniz helped pioneer, to find the path of least action for light and particles. We are literally living in a world optimized by the mathematical principles Leibniz derived. Before we conclude this journey through the mind of the last universal genius, if you have learned something new about the origins of the math you use today, please hit that like button. Sharing this video helps us bring the stories of these incredible thinkers to a wider audience. And if you haven't already, subscribe and turn on notifications so you never miss an episode of our mathematical history series. Gottfried Wilhelm Leibniz died with only his secretary by his side, but today, he is accompanied by billions of people. Every time you turn on a computer, every time you use a calculator, and every time a student writes a dy divided by dx on a chalkboard, Leibniz is there. He wasn't just a mathematician. He was the architect of the information age. He showed us that the universe is not just a collection of matter, but a collection of information, logic, and harmony. As he famously said, to love is to find your own happiness in the happiness of another. Perhaps he would be happy to know that his dry formulas and strange zeros and ones have become the language of human progress. Thank you for watching and see you in the next video.